Hey everyone, hope this video finds you well. Today we're going to be talking about HNMR, right? And so you may be asking yourself, what is the goal of HNMR, right? So the goal of HNMR is to figure out the structure of something, right? There's different ways that HMR is generally used, right? The first, I probably say one of the most common ways HMR is used, right, is by chemists to help prove that the molecule that they made is actually the molecule that they made, right? For example, if you publish in a paper that I think reactants, if you take reactant A and you give reactant A, you put it in with reactant B, you'll get product C. Well, you can say that in a paper, right? You can do the mechanism, you can justify it on paper, right? But the real meat of your proof, right? The evidence you're going to use to back up your findings in chemistry is going to be from HNMR, right? You're probably sure you guys have probably used like IR spectroscopy, mass spectrometry in the past, but HNMR is truly like the gold standard. I would argue the gold standard for trying to figure out what your structure is, right? Because I'm sure as you guys know, from previous OChem labs, you guys have thought that you made a certain product when in reality it was actually another product instead, right? And so you don't have minute 120% control over how the reactions, how different type of chemical reactions will go. So you just got to do it to make sure. But the second way, probably the second way that I know HNMR is being used, right, is with let's say for example, right, for law enforcement, right? If you're a lab that's just been sent like a what you call it, if it's just been sent like a weird sample of white powder, right, and the police want to know, is this cocaine or something, right? So yeah, that's another way they can use it as well. So let's kind of talk about the rough and dirty my rough and dirty explanation of HNMR. It isn't, well, it doesn't account for 120% about like the actual physics behind HNMR, but I think it's good enough for the purposes of this class. And I think if you're just here trying to pass and or trying to do well, I think it'll just do just for you. So as you can see here, right? Oh, by the way, I forgot to mention this is what you're going to be looking at, right? You're going to be given a spectra like this, and you're going to be asked to, all right, I want you to give me the structure of this. Alrighty, cool. So the way HNMR works, right, is that first of all, you have your molecule, right? You throw it to an HNMR machine, right? And then you have an applied magnetic field. Applied magnetic field. I'll abbreviate it as AMF, right? Super strong magnet, apply that magnetic field to it. And then from there, the electrons that are within, right, will start to spin around a circle like this, right? And they're spinning due to due to a super nerd reason, physics, right? Sorry, I'm not a physics person. It'll generate an induced magnetic field. Induced magnetic field. Magnetic field, or IMF, right? And then from there, right, you have hydrogens that are in there, and depending on their unique chemical environments, right? Due to the unique chemical environment, what's going to happen is that those hydrogens are going to be exposed to various points, right, of the applied magnetic field, and then and the unique chemical environments, right, will affect their the way they react to the applied magnetic field, right? Hold on, hydrogens just will affect how they react to applied magnetic field. Yep. So, and then from there, right, depending on the different unique chemical environments, right, you can then discriminate between different types of hydrogens, right, different types of HNMR signals, and then from there you can piece together the structure. So if you want super hard details about how it kind of works, I would talk to Dr. Ko about this, right? But B, so you have an applied magnetic field, right? That leads to an induced magnetic field. Sorry, wait. Sorry. It leads to electrons moving around. Step there. Electrons encircle. I can't spell. Yikes. Electrons encircle. And then you have an IMF, right? You have your induced magnetic field. And then from there, right, hydrogens get affected due to their unique chemical environment. And then from there, you're able to kind of parse out what the structure will be. Alrighty, is this the most scientific explanation as to how HNMR works? Nope, but this is the way I understood it, and I came out of 8B with an A, so works there at least. If you want more in-depth explanation, talk to Dr. Ko about it. Anyways, so there's a couple of different steps that you kind of have to get when it comes to doing HNMR, right? And I'll put these in order of how important I think they are. And so the first two, right, are going to be the number of signals and then splitting, right? And then from there, we'll move on to the other steps right here. So the number of signals, right? HNMR signals is very, very important, right? If you have, let's say, for example, 12 hydrogens in a structure, does that mean you'll get 12 different signals? No, not really, right? And so, yeah, as you can see up here, right, there's 1, 2, 3, 4, 5 signals, right? And so how do we determine that there's 5 signals in that spectra or like a certain numbers of signals in another spectra? Well, the quick and dirty rule is symmetry. Symmetry, 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 symmetry. All right. So if you have a symmetric molecule, right, what you can generally do, right, is that you can, right, I'll draw the H's here. Right. And then you can kind of draw groups across here, right? So you can kind of draw groups across, right? And you can say 1, 2 signals, right? And so this is the really, really quick way to do it, right? But this rule of symmetry won't it won't work 100% of the time, right? And so instead, kind of the golden rule, right, is going to be something called unique chemical environments. Right? Right? And so, right, instead of doing the quick way, right, with symmetry, right, let's quickly kind of break this down, right, and talk about unique chemical environments. So let's analyze this CH3 right here, right? I'll highlight this in yellow. So let's ask ourselves, right? What's the chemical environment that this CH3 and the hydrogens on it, right? Where does it find itself? It looks up, right, towards its neighboring carbon, and it sees a CH2. Okay, it sees a CH2, right? It looks to its right, looks down. There's nothing else there, right? I mean, the only thing that really matters in this case would be neighboring carbons, and well, it only sees a CH2. It's a CH2 from that angle. Now, coincidentally, right, this CH3 right here is also in the same position too, right? It looks up and it sees a CH2. And so as you can see here, right, even though symmetry can kind of help you see it, right, the real reasoning behind it, behind why the symmetry kind of works, is because that these two CH3s, right, are in the same chemical environment with each other, right? That CH2 is basically like the same CH2 that the other CH3 sees. Okay? And the same thing happens, right, with these CH2s on top. Right? Right? These guys, they look down and all they see are two CH3s, right? This guy over here, right, looks down, sees a CH3, right, and looks to its left, right, and sees another CH2 in the same exact position as it is. And this guy over here looks down, sees a CH3, looks to its right, sees a CH2. Okay, these guys have the exact same chemical environment, so they're all belong to one signal. In total, there are 2 signals here. Things get really, really easy, right, when it comes to this unique chemical environment if you have an asymmetric molecule. If you have something along the lines of this, right? Let me draw this right here. The H is out here. There's no plane of symmetry, no matter how you slice it, right? And as you can see here, right, also based off of the unique chemical environments here, right? There's I want you guys to pause, think to yourself, right? Pause the video and think to yourself, okay, how many chemical environments are there, or how many signals are there going to be? Alrighty, cool. So as you can see here, right, this CH3 is totally on its own because it looks, the only thing that it can look at, right, it looks to its left, it sees a carbonyl, and that's pretty much it. This CH2, right, is the only CH2 here. And on top of that too, it looks to its right, there's a carbonyl, looks to its left, there's a CH3 there. And so this CH2 is going to be on its own. And then you have this last CH3 over on here. I'll highlight this in purple, right? It looks to its right, it sees another CH2. So these are three unique chemical environments, right? Because, well, there's no other like CH2s or CH3s that are in the exact same position with the exact same chemical environment as it is, right? And so there's going to be three signals here, three signals, one for each color, right? And but the quick way is to just literally just think to yourself, okay, if it's asymmetric, right, then most likely all the H's are going to be all the groupings of hydrogens are going to be different signals. Yeah, so this is asymmetric, right? So in summary, right, you can drew a plane of symmetry and figure out how many signals there are mostly. That'll work in most scenarios, but when it comes to this more intricate, I would say when it comes to more intricate structures, then you might have a little bit more trouble. Let me give you an example here. This is a little hexane here, right? And sorry, cyclohexane. I apologize. So this cyclohexane is symmetrical, no matter how you slice it. As long as you slice it in equal halves, there's like no way you can get an asymmetric cut. And so maybe thinking to yourself, okay, this CH2 right here. There's CH2 right here too, CH2 right here too. Now let's ask ourselves, how many signals are in this structure? How many HNMR signals are in this structure? I'll give you guys some time to figure that out. Okay. So you might be thinking to yourself, maybe I can use symmetry here. I can use symmetry here. And I can group this like this is one signal right here. Maybe this is two signals right here. You may be thinking to yourself, yes, that makes sense. And I would too. If I was in your shoes, when I was first in your shoes, I thought that way too. However, this is one of those times where you have to think about the unique chemical environments. And so let's talk about this CH2 right here. All right, so let's analyze it. To its right, you see another CH2. To its left, you see another CH2. Wait a second here. No matter which CH2 you decide to analyze, if you look into its perspective, there's the same CH2, the exact same CH2 on every single side of it. There's literally nothing here. Imagine if you lived in a neighborhood, but instead of different people living in the neighborhood, it's just the same person, just a clone of you, following the exact same schedule, exact same thoughts. There is no unique neighborhood. There's no unique chemical environment. So the only option that we have when it comes to making statements about the chemical signals here is that they're literally all the same. And when they're all the same, it means that there's literally only one signal. All of these CH2s belong to one signal, not because of symmetry, right? Symmetry didn't really help us in this scenario, but because of the unique chemical environment perspective, right? Now, things do, if you kind of throw off the symmetry just a little bit, let's put a CH3 here, yeah? So let's look at this, right? How many signals would there be? I want you guys to kind of go ahead and figure that out on your own. Okay, cool. And just remember, there's an H here too. It's implied. But in this case, the H's here, this whole molecule isn't, this whole structure isn't really symmetrical all the way around. There's certain ways you can kind of cut it where it isn't symmetrical, but overall, it is symmetrical. And so in a case like this, where you have substituents on a ring, generally you can kind of do the symmetry rule, and you'll end up with, go ahead, I'll end up with, I believe it was a 1, 2, 3, 4, 5. You'll end up with 5 unique signals. And so we'll talk a little bit more about that in a second. So yeah, so I colored these different colors right here. And this is the point where the unique chemical environment rule gets it gets a little fuzzy here, right? There's some slight nuances here. So this CH3 is obviously on its own. There's no other CH3 here. That's a very, very unique chemical environment here. There's a CH here. That's very unique as well. Now, once we get into here, right, it's obvious that these CH2s, right, are on their own, right? Because they look up, they see a CH. They look down, they see a CH2. Same vibe over here. And so these are on their own. Now, let's look over here. Now, some people might be a little bit confused about these CH2s right here. Why is it exactly 2 signals on their own between these here, right? Because if you look, this CH2 from here, it looks up, it sees a CH2. It looks over here, it sees a CH2. From this guy's perspective, the purples look down, they see a CH2. They look up, they see a CH2. Wait a second, shouldn't these guys, right, be the exact same chemical environment with each other, therefore the same signal? Well, not exactly. This CH2 is a little bit different than this CH2. Why? Because this CH2 is next to a CH, and this CH2 is just kind of just there on its own. It's next to other CH2s. So this is where you kind of have to use a little bit of your brain, a little bit. You can't just turn your brain off and just use symmetry, right? I know human beings are really good at recognizing patterns, but sorry about that. No evolutionary psychology for you here, right? You have to keep in mind that some of these CH2s can be slightly different to each other, right? Based off of other things that are surrounding it, which is why we don't really go off of like, oh, if it's a CH2 next to another CH2 next to another CH2, it must be like, the same CH2. Not necessarily, right? You have to take into account that unique chemical environment rule. Alrighty, I have said the unique chemical environment like 6 bajillion times here, but this is the really, really important part of HNMR, figuring out the number of signals there are. There's going to be a lot more, what would you say? There's going to be a lot more practice with this later on, but this is the base stuff you should know so far. If it's asymmetric, don't even worry about it. Most likely that every single signal is probably different. So, alrighty. So please make sure to practice this. If you don't get it, well, I have bad news for you because the foundation of HNMR is trying to figure out where exactly the number of signals are. Next thing here, we're trying to talk about splitting. As you can see here, the HNMR signals show up as like these kind of little stalagmite, the things you find in caves, the little spiky stuff. And so what determines splitting? Well, that's a great question, right? So splitting is essentially going to be, it's going to go into what does the signal look like, right? What does it look like? And so there's different types of signals that you can get. You can get singlets, right? It's like a single stalagmite, singlet. And these all follow a very, very conventional naming scheme. So you have a doublet here. And you can have a triplet here. And you have a quartet. And then you can go on with the quintets, quintet, sextet, septet. I think I know my numbers. Yeah. And then it just keeps on going until you have you can have like some signals are just like this. It's like a bunch of spikes and you can't even tell what the hell it is, But for the most part, I think 80%, 90% of all you're going to be dealing with is going to be singlets, doublets, triplets, and quartets. All right, cool. So let's kind of redraw one of the molecules that we used earlier. Here. All right, tell me how many signals there are in this. Okay, assuming that you paused the video and you did. There's 3 signals here. Yep. 1, 2, 3. Okay, cool. Alrighty, so with this, these signals right here, right? How do we determine whether or not these signals are going to show up as singlets, doublets, triplets, or quartets in your HNMR spectrum? Well, let's figure it out. The golden rule here is going to be n plus 1. I have no clue what n formally stands for, but I like to imagine it's neighbors. So just pretend n is neighbors. So the n plus 1 rule basically states that from your perspective of whatever HNMR signal you're trying to analyze, how many hydrogens are on the neighboring carbons. So you look over here, right? This H, sorry about that. My alarm went off. So these H's right here, right? They look over to the left here, right? That's the only neighboring carbon they have. Are there any hydrogens there? No. And it stands to show that this little carbon, right, this carbonyl right here that I'm circling, won't have an HNMR signal. Why? Because there's no hydrogens. Basic rule, right? That makes sense. No hydrogens, no HNMR, right? If you have no flour, you can't make a cake. Type shit like that. All right, n plus one. So what's the number? What's the number of neighbors that it has? Zero. Zero plus one equals one. Oops, equals one. That's going to be a singlet, right? Because singlet is one. Single. Singlet. You can do the same thing over here, right? Let's do blue, right? I'm gonna move this down a little bit more. Blue. N plus one, right? How many neighbors does it have? I count one, two, three. Right? 3 plus one equals four. Four is a quartet, right? What's quartet? So it's going to be something along the lines of this. Oh, and I forgot to draw this over here. Singlet. Oh, yeah. Alrighty. And so let's analyze the ones down here, right? N plus one. How many neighbors does it count? One, two. 2 plus 1 equals 3. Triplet. Yep. Simple as that. So that's how splitting generally tends to work. There's going to be some really, really wacky exceptions later on, but this is essentially it. This is like you'll deal with most situations like this. Mm-hmm. Alrighty, cool. So another thing, right, is going to be where signals show up. I don't know if you guys noticed, but back up here, right, we were looking at this. Certain signals will show up a little bit further down or further up. Why is that? What determines where they're going to end up at? I'm glad you asked that. People sometimes get fixated on this, right? Because sometimes Dr. Ko will say, this structure tends to show up around this area. And people, a lot of people, including myself, will sit there and be like, oh crap, I have to memorize like a million shifts, right? Like where these signals show up. And I mean, I guess it's useful for some scenarios, right? If you have like an aldehyde, so some shifts are very, very noticeable. But at the end of the day, it's like a losing game. There's like a billion different scenarios, right? That can change the way like think where things show up. So I wouldn't don't memorize signal shifts. It's better that you kind of use your logic and figure that out from there. Okay. Alrighty, cool. So when it comes to where signals show up, yeah, we're going to go ahead and we're going to. It's basically very simple, right? It's a question really of electronegativity. Right? And so if we draw a spectra this way, right? We have 0 here, 12 here, right? Just in the middle, right? So this is what a HNMR spectrum looks like, and the units are, I believe, in ppm, right? And so the way this generally tends to work is that there's a couple phrases that you need to know. Signals that show, wrong color. Oops. Signals that show up down here are going to be considered downfield or less shielded. Over here, if they show up on this side, it'll be more shielded or upfield. Yeah, this is relative to each other. These are like adjectives that you can use to describe. For example, if I do this purple signal right here, and I have this black signal right here, yeah, there's different colors. I can say the purple one is more upfield than the black one. I can say the black field is more downfield than the purple one, or vice versa. I can say that the black is less shielded, or I can say the purple is more shielded. It depends on how you want to say it, right? Yeah, it's up to you, but get used to using these phrases a lot. And so when it comes to electronegativity, right, and how that plays into it, if I drew some lines of this, right, it's a question of basically proximity for the most part, right? So, all right, cool. I drew the structure right here. How many signals do you think this is? Take a wild guess. All righty, Cool. So you guys hopefully recognize that this is asymmetric molecule, and therefore each of these signals has its own has each one of these groupings of hydrogens has its own signal. There's one, there's two, there's three. And this one's a maybe. Four is a maybe, right? If you said four, that's fine. But generally, if you throw a sample of HNMR structures, of HNMR, sorry, if you go into an HNMR sheet, a bunch of structures that have OH or NH, right? OH or NH, there's actually no guarantee these will pop up. There's no guarantee these will pop up in HNMR. Why? Well, the reason why there's no guarantee these will pop up in HNMR is because well, generally because of acid-base nonsense, right? These H's will like exchange H's with each other, right? So yeah, there's no guarantee these will pop up. Dr. Cole will probably tell you more about this in class. But assuming that they do, right? There's going to be four signals here. And when it comes to ranking them, right? If we had to rank them from the most downfield, purple, right, would be the most downfield. You'd find this furthest to the left. And then from there, it would be followed by, actually, I probably should have chosen a different color for this. I don't know if you can tell. Anyways, this is going to be yellow. Right? So you find that there. And then three would be the third most downfield, and red would be the most upfield, right? So you'd find them, this is not accurate to scale, right? But you'd find them something along the lines of this. You'd find purple somewhere for the furthest to the left, yellow somewhere there, and then blue somewhere here, and then this over here somewhere, right? When it comes to the overall scale, right? Different ways you can slice it here. Yeah. And keep in mind, this isn't where these will normally show up at. I'm just saying this as like a just to show you that like the most downfield will generally be the closest to the electronegative atoms. And as you learn more, right, there's going to be more scenarios, right, where you can very intricately kind of pick out, okay, which one of these would be the most downfield. But this is the major things you're going to deal with: electronegative atoms, C double bond O, nitrogens, bromines, fluoride, chlorine. Those are going to be the ones that are going to be really dragging stuff all the way to the left. So that's fun. Anyways, and then from there, we're going to talk about, this is probably the easiest of all, but I've messed up this explanation before. So let's be, well, not splitting. let's be a little cautious here. This is going to be integration. All this does, it answers the question, how tall will a signal be? How tall will the signal be? Right? Because I'm sure as you guys notice up here, right? Different signals are different lengths. This one's really, really tall. These guys are very, very short. Yeah. People may tell you height doesn't matter, but in HNMR chemistry, it does. Definitely does. So yeah. Anyways. So let's see here. Let's give you guys an example. But basically the logic is very, very simple. I think it's very simple. Right? If I do something along the lines of this, right? So I want you guys to quickly kind of go and figure out how many signals there are in this. Okay, cool. So for these H's right here that I just drew, right? These guys right here. I'm just gonna do let me just put CH3. I don't have any space for this. Right? Let's see here. Those guys are one signal. These guys are one signal, and then this little aldehyde H, it's one signal too. That's too bright. I can't see crap. Okay, cool. All right, that's one signal on its own. Now you maybe ask yourself, wait a second. Wait, how are these all one signal, right? Well, think about their unique chemical environment. They look down. There's a carbon that's fully substituted. Carbon there fully substituted. There's nothing else there. And yeah, these are all kind of one thing on their own. And on top of that too, right, the CH2 is kind of on its own, and then this little H over here is on its own as well. Alrighty, cool. So the way that chemists tend to figure out how many signals belong to a certain signal, right, is by doing math, by doing integration, right? And if you remember integration, it's area under the curve. So the more hydrogen that you have belonging to a certain signal, the more area that will be under the curve, right? So more hydrogens, area under the curve, mole area under curve. And then it basically means that the signal shows up as taller signal. The way I would draw this, right, is that, let's see here. This would be here, right? The red signal will be here. The blue will be sometime here. And then the yellow will be right here. These are all singlets because there's no other ones there. Yep. And so, yeah, you can basically tell, right? Because there's like what, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9 signals belonging to this one signal. So therefore it would be the tallest. There's certain ratios too, like maybe 3 to 1, 1 to 6, right? But like at the end of the day, right, the quick way to do it is that just, more H's, taller signal. So that's all the stuff I have for you today. Hope you guys are studying well, and I'll see you all sometime later. See ya.